Our planet's sky feels like a known quantity, a vast but familiar ceiling to our world. We look up and see the predictable arch of a bird's wing, the distant glint of an airplane tracing a line across the blue, the fleeting, almost invisible passage of an insect. It is a domain we believe we understand, one governed by ruthless and unwavering rules of physics. We have convinced ourselves that weight is a constant tyrant and that flight is a hard-won, delicate victory of biology or engineering. And based on everything we see around us today, we have come to accept what we believe are the absolute upper limits of what can fly. But this entire perception, this bedrock of our understanding, is built on a profoundly and deceptively limited sample of time. We are living in a biological whisper, a quiet aftermath that is but a faint echo of an age when the sky was not merely occupied, but ruled by titans. This was an age when the known laws of physics seemed to bend, to accommodate creatures of a scale so enormous it borders on the mythological. It was an era when the shadows that swept across the land were cast not by clouds, but by living, breathing mountains of flesh and bone that had utterly mastered the air. This is the story of a lost blueprint for life itself, a set of biological secrets for conquering the sky that our world has, for 66 million years, failed to replicate. And it is a search, not just into the deep past to uncover what was lost, but into the future, to ask a thrilling and vital question. Where might that blueprint reappear? Not in the fossil record, but in the world to come. Our journey back in time takes us to the late Cretaceous period, a world that would be almost unrecognizable to us. The continents were in different positions, the climate was a humid, global greenhouse, and vast, shallow seas divided the landmasses. And in the skies above this alien world soared the undisputed masters of the air, the pterosaurs. It is crucial to understand what these creatures were, and what they were not. They were not dinosaurs, though they lived alongside them, and they were certainly not birds, their distant evolutionary cousins. Pterosaurs were a completely distinct and spectacularly successful group of flying reptiles, a dynasty of aerial predators that had first taken to the air 230 million years ago, launching the age of vertebrate flight tens of millions of years before the first feathered dinosaur even conceived of leaving the ground. For over 150 million years, they diversified into a breathtaking array of forms, from creatures the size of a modern sparrow to the true giants that obliterate our modern sense of scale. The pinnacle of this lineage, its final and most magnificent creation, was a creature that emerged near the very end of the Cretaceous. Its name, drawn from the Aztec serpent god of the sky, is as epic as the animal itself, Quetzalcoatlus northropi. To speak its name is to invoke a scale that feels more like a legend than a biological fact. Its story in the human world began in 1971, in the arid badlands of Big Bend National Park, Texas, when a 22-year-old graduate student named Douglas Lawson stumbled upon a fragment of bone unlike anything seen before. The bone was hollow and shockingly light, yet its size was immense. At first, its identity was a mystery, but as Lawson and his supervisor, Juan Langston Jr., excavated further, they unearthed more fragments of a partial wing. The pieces began to click into place, and a terrifying and awe-inspiring image emerged. They were looking at the remains of a pterosaur, but one of such colossal proportions that it shattered every existing record and expectation. The scientific community was stunned. The fossils painted a picture of an animal that, when standing on the ground, would have looked a giraffe in the eye. It was a predator whose head alone was nearly 2 meters long, perched atop a long, impossibly elegant neck. It was, by any measure, a giant. But its true majesty, the feature that would make it a legend, was only revealed when paleontologists began to reconstruct its wings. With a wingspan that stretched between 10 and 11 meters, 33 to 36 feet, from tip to tip, Quetzalcoatlus was not merely the size of a small aircraft. It was functionally a living airplane. Its wingspan was wider than that of a Cessna 172, a four-seater aircraft common at any local airfield. It was an organic glider, a living machine of flesh and bone that could, according to some studies, potentially stay aloft for a week or more at a time, crossing entire continents by soaring on thermal updrafts, covering hundreds of miles with barely a flap of its colossal wings. Try to form a picture of this creature in the world it inhabited. Imagine it stalking through a fern-covered floodplain, its long, toothless beak, which its discoverers nicknamed chopsticks, probing for small dinosaurs and other vertebrates. Then imagine the launch. It was not a graceful, running takeoff like a bird's. Biomechanical models show that for a creature this heavy, weighing an estimated 250 kilograms, that would be impossible. Instead, using a technique now called a quadrupedal launch, Quetzalcoatlus would crouch, then explosively vault itself into the air using the immense power of its hind legs and its powerful, folded forelimbs simultaneously. It was a biological pole vault, a single, catastrophic burst of energy that propelled its entire mass upward and forward, giving it just enough height and airspeed to unfurl its vast wings and catch the wind. The existence of Quetzalcoatlus and its close relatives, the giant Azhdarchids, confronts us with a profound biological and physical paradox. How could an animal of this size generate enough lift to overcome the relentless pull of gravity? How could its bones, which were famously thin and hollow, withstand the immense stresses of a powerful launch and the constant flexing of flight without shattering into 1,000 pieces? Our own best aeronautical engineers, armed with advanced composites like carbon fiber and sophisticated computer-aided design, still struggle to build flying machines with the same relative efficiency, resilience, and payload capacity. And yet, here was nature 66 million years ago, having already perfected a design that still sits at the very edge of what we consider theoretically possible. This, then, is the central mystery that will drive our entire investigation. The fundamental laws of physics have not changed. The force of gravity has not weakened. The principles of lift and drag remain the same. Yet, the biological blueprint for constructing a living creature on the scale of Quetzalcoatlus has, for all intents and purposes, been lost to time. Today's sky is conspicuously empty of such titans. The largest flying bird alive today, the magnificent wandering albatross, has a wingspan of just over 3.5 meters. It is a master of the air, but it is a dwarf when compared to its prehistoric predecessor. Something fundamental has changed in our world. An evolutionary doorway that was once thrown wide open, inviting life to achieve its maximum aerial potential, has seemingly been slammed shut, bolted, and locked. To understand what the future of flight could possibly hold, we must first look back with the combined eyes of a detective and an engineer. We must decode this lost blueprint, piece by piece, from the fossilized evidence. We have to ask the hard questions. What were the unique environmental conditions and evolutionary innovations that allowed these giants to arise in the first place? What were the intimate secrets of their impossible biology? And perhaps most critically, what catastrophic event or gradual pressure caused them to vanish so completely from the face of the earth? Because only by answering these questions, only by understanding how that door was closed, can we begin to ask the most exciting question of all. Could it ever be opened again? To truly comprehend the giants of the prehistoric sky, we must abandon our modern intuition about what is biologically possible. The body of a giant pterosaur was not simply a scaled-up version of a bird or a bat. It was a completely different solution to the fundamental problems of flight. It was a masterpiece of biological engineering, an anatomy forged in the crucible of a 150-million-year-long aerial arms race. Every single part of its skeleton, every muscle, and every ligament was a finely tuned compromise between two ruthless and opposing demands: the need for immense structural strength and the absolute non-negotiable necessity of being almost impossibly lightweight. It is within the elegant resolution of this central conflict that we find the first key to unlocking their impossible biology. And there is no better place to start this investigation than with the most dramatic and controversial feature of creatures like Quetzalcoatlus: their astonishingly long neck. For decades after their discovery, the necks of giant Azhdarchid pterosaurs were a source of intense scientific argument, a feature that seemed to defy the basic principles of flight mechanics. In some species, the neck stretched for over 3 meters, a length greater than that of a modern giraffe. To a flight engineer, this is a nightmare. A long, heavy neck would dramatically shift the creature's center of mass forward, creating crippling instability. It would be like trying to throw a javelin by holding the very end of its tail. The entire system would want to pitch forward and tumble out of the sky. Furthermore, for an active predator, Such a long and seemingly delicate structure would appear to be a fatal flaw. How could it possibly withstand the violent stresses of striking at prey, or even just the strain of its own weight without buckling? For a long time, the prevailing theory was that these animals must have had severely restricted movement, forced to hold their necks in a stiff, straight line. But the truth, revealed not by speculation but by looking inside the bones themselves, was infinitely more sophisticated. Using high-resolution CT scanners, the kind you would find in a modern hospital, paleontologists peered deep inside the fossilized cervical vertebrae of an Esdarchid. What they discovered was an architectural marvel. The central neural tube, the hollow channel that once housed the spinal cord, was not merely floating in the middle of a hollow bone. It was meticulously connected to the vertebra's outer wall by a dense, intricate web of fine bony struts called trabeculae. These filaments, some no thicker than a human hair, were not randomly arranged. They were organized in a precise, helical pattern, crisscrossing the interior of the bone like the spokes of a bicycle wheel or the support trusses of a suspension bridge. This was not bone. This was a biological metamaterial, a composite structure designed for maximum strength with the minimum possible mass. This was the impossible solution. The genius of this design cannot be overstated. The helical arrangement of the trabeculae provided immense resistance to bending, compression, and torsion from any direction. Computer modeling has shown that as few as 50 of these delicate struts were enough to increase the neck's resistance to buckling by an incredible 90%. This meant the pterosaur's neck was not a clumsy, fragile appendage at all. It was a feat of biological lightweighting, a structure that was simultaneously long, strong, stiff, and yet mostly composed of air. It allowed these creatures to wield their enormous heads with speed and precision, striking at prey on the ground below, all without compromising their ability to fly. This single discovery transformed our understanding of these animals, from awkward, delicate gliders to highly efficient and powerful predators. It's a design that aerospace engineers, striving to create the next generation of lightweight materials, are now studying with intense fascination. This principle of extreme lightweighting, technically known as pneumaticity, was not confined to the neck. It permeated the entire skeleton of a large pterosaur. Their bones were not solid rods but thin-walled, hollow tubes, often with bone walls less than a millimeter thick. But they were not fragile. They were internally braced and strategically thickened at points of high stress. This made their skeletons almost unbelievably light. Current estimates suggest that the entire skeleton of a Quetzalcoatlus with a 10-meter wingspan weighed only about 15 kilograms, less than a small child. The vast majority of its 250-kilogram mass was the engine, the muscles, organs, and the vast, powerful wing membranes. Of course, a lightweight skeleton is useless if you can't get it off the ground. The second key to their success lay in their unique and incredibly powerful launch mechanism. For a long time, paleontologists, influenced by modern birds, imagined pterosaurs launching by running to build up speed and then leaping into the air. But as our understanding of their size and weight grew, biomechanical models showed this to be a fantasy for the larger species. A 250-kilogram animal simply cannot generate enough power from a running bipedal start. The stress on its ankles would have been immense, and the physics just didn't work. The answer to this puzzle came from a different line of evidence: fossilized trackways and the robust structure of their forelimbs. Unlike birds, whose powerful legs do all the work on the ground while their wings are specialized solely for flight, pterosaurs were quadrupedal. They walked on all fours, using their long hind limbs and their powerful folded forelimbs. Their arm and shoulder bones were incredibly robust, far more so than a bird's. This anatomy, which initially seemed awkward, was actually the secret to their explosive power. Instead of a running start, a giant pterosaur would crouch, then vault into the air using the combined, synchronized power of its muscular hind legs and its massively powerful forelimbs. It was a quadrupedal launch, a biological pole vault that propelled its immense body upwards and forwards in a single catastrophic burst of energy. This method is vastly more powerful than the bipedal launch of birds, and it is what allowed creatures on the scale of Quetzalcoatlus to break the bonds of gravity from a dead stop. Finally, we come to the wings themselves, which were far from simple flaps of skin. A pterosaur wing was a complex, dynamic, and highly controllable airfoil. The primary wing membrane, or brachiopatagium, stretched from the tip of a dramatically elongated fourth finger all the way back to the ankle. But this was just one part of a larger system. A unique bone, found only in pterosaurs, called the pteroid, projected forward from the wrist. It supported a forward membrane, the propatagium, which acted like the leading-edge slat on an airplane wing, preventing stalls at low speeds and increasing lift during takeoff. The entire wing system was a living fabric, not just skin, but a composite of muscle layers, blood vessels, and a dense network of fine, stiffening fibers called actinofibrils. These fibers, like the battens in a modern high-performance sail, prevented the membrane from fluttering or tearing and allowed the pterosaur to subtly change the wing's shape or camber in mid-flight. This gave them an unparalleled level of flight control and aerodynamic efficiency. Hollow bones reinforced with an internal space frame, a powerful quadrupedal launch that defied conventional wisdom, and dynamic, shape-shifting wings controlled by a unique skeletal architecture. These were not just individual adaptations. They were a tightly integrated suite of evolutionary solutions that worked in perfect harmony. They were the core components of the lost blueprint, the biological secrets that allowed life to conquer the sky on a scale that seems impossible to us today. They were the product of 150 million years of relentless evolutionary refinement, a pinnacle of aerial design. And then, in a geological heartbeat, they were all gone. For an astonishing 150 million years, the pterosaurs were an enduring dynasty, the undisputed sovereigns of the global sky. Their fossil remains, unearthed on every modern continent from the frozen wastes of Antarctica to the plains of North America, tell a story of incredible success and remarkable adaptability. They were not a fleeting experiment. They were a cornerstone of the Mesozoic world. But their very success was intrinsically tied to the stability of that world, a warm, vibrant greenhouse ecosystem teeming with life. Their reign was brought to a sudden, incomprehensibly violent end not by a superior competitor or a gradual evolutionary decline, but by a cataclysm from beyond the earth. The story of their disappearance is not a slow fade to black. It is the story of a global reset button being slammed down, an event that wiped the slate of life so clean that it created the conditions for a completely different kind of sky to emerge from the ashes. The agent of this reset, which occurred with chilling precision 66 million years ago, is known to science as the Cretaceous-Paleogene or KPG extinction event. It was triggered by the impact of an asteroid, a rock some 10 to 15 kilometers in diameter, traveling at cosmic speeds. It struck the planet in the shallow, tropical waters of what is now the Yucatan Peninsula in Mexico, creating the now-buried Chicxulub crater. The immediate effects were apocalyptic on a scale that is difficult for the human mind to grasp. The impact released energy equivalent to billions of nuclear bombs, vaporizing the asteroid and a huge chunk of the Earth's crust in a fraction of a second. A shockwave of unimaginable force radiated outwards, triggering earthquakes of a magnitude never since recorded and megatsunamis hundreds of meters high that scoured coastlines thousands of miles away. But these were just the opening salvos of a far more insidious and long-lasting global catastrophe. The initial impact also generated a thermal pulse, a wave of intense infrared radiation that briefly superheated the atmosphere. This pulse was so intense that it is believed to have ignited global wildfires, incinerating vast swathes of the planet's forests. The true killer, however, was what all this chaos threw up into the sky. The impact ejected a colossal plume of pulverized rock, dust, soot from the global fires, and, critically, sulfur-rich aerosols from the vaporized seabed rocks. This material was blasted high into the upper atmosphere, where it spread rapidly around the globe, enshrouding the entire planet in a thick, toxic blanket of darkness. This was the infamous impact winter. For months, perhaps even years, sunlight could not penetrate the thick atmospheric haze. On the surface, the world was plunged into a perpetual freezing twilight. Without sunlight, photosynthesis, the fundamental process that converts light into life and underpins almost every food chain on the planet, ground to a halt. The world's plants, from the microscopic phytoplankton in the oceans to the towering forests on land, withered and died. The great ecological engine of the planet simply shut down. For the animals that depended on these plants, the herbivores, it was a death sentence by starvation. And for the carnivores that hunted the herbivores, their fate was sealed. The entire global food web collapsed, starting from the bottom and working its way relentlessly to the top. For the giant Azhdarchid pterosaurs like Quetzalcoatlus, this was an inescapable trap. As apex predators, they sat at the very pinnacle of a complex and vibrant food web. As we've learned, they were likely terrestrial stalkers, striding through the prehistoric plains and forests like giant, winged storks, picking off small dinosaurs, lizards, and other vertebrates. Their entire lifestyle was predicated on a rich and abundant supply of this medium-sized prey. When the impact winter triggered the collapse of the ecosystem, that supply didn't just dwindle, it vanished almost overnight. The scale of the pterosaurs, for so long their greatest evolutionary asset, instantly became their greatest liability. Large, warm-blooded animals require a prodigious amount of food to fuel their high metabolism. A 250-kilogram flying predator needs a constant and reliable source of calories to survive. In a world suddenly plunged into darkness and starvation, the giants are always the first to fall. There was simply nothing left for them to eat. This narrative of a sudden, catastrophic end seems clear-cut. However, for many years, a competing scientific theory suggested a different story. Some paleontologists argued that pterosaurs were already in a long-term, gradual decline for millions of years before the asteroid impact. The evidence for this was a perceived drop in pterosaur diversity in the late Cretaceous fossil record. According to this gradual decline model, competition from the newly evolving and highly adaptable birds was slowly pushing the pterosaurs out of their ecological niches. The asteroid, in this scenario, was not the sole killer but merely the final, merciful blow to a dynasty that was already fading away. However, more recent discoveries have dramatically challenged this view. The fossil record is notoriously incomplete, especially for delicate, hollow-boned creatures like pterosaurs. An artifact of this incompleteness, known as the senior lips effect, can make a sudden, catastrophic extinction event appear gradual in the rock record. Furthermore, stunning new fossil finds from the end of the Cretaceous in Morocco have revealed a surprise. Right up to the geological moment of the impact, the skies of North Africa were filled with a remarkable diversity of pterosaurs, at least 7 different species from 3 distinct families, ranging in size. This suggests that, far from being a dying lineage, the pterosaurs were thriving and diverse. They did not fade away with a whimper. They were cut down in their prime with a cataclysmic bang. This still leaves us with a critical question. If the pterosaurs were thriving, why did they perish completely while another group of flyers, the birds, managed to survive the apocalypse? The answer likely lies in a combination of size, diet, and lifestyle. The birds that made it through the KPG boundary were not the majestic eagles or vultures of today. They were small, likely ground-dwelling creatures, similar in habit to modern quails or tinamous. Their critical advantage seems to have been their diet. Many of these early birds had beaks adapted for eating seeds. In a world where green plants had vanished, a vast larder of dormant seeds would have remained in the soil, providing a crucial, accessible food source that was unavailable to the carnivorous pterosaurs. They were survivalists, able to live on the scraps of a broken world. Furthermore, their small size and lower metabolism meant they needed far less food to survive. They could find refuge in burrows or dense undergrowth, sheltering from the harsh conditions of the impact winter. The giant pterosaurs had no such refuge. Their enormous size, their specialization as apex predators, and their high-energy lifestyle made them exquisitely vulnerable. They were magnificent engines tuned to perfection for a high-performance world. But when the fuel supply was cut off, they were the first to stall and fall from the sky forever. The extinction of the dinosaurs on land and the pterosaurs in the air was therefore a profound and violent turning point in the history of life. It was the ultimate Great Reset. It didn't just remove a few species. It decapitated the entire global ecosystem, clearing the board of its dominant players and creating an almost unimaginable power vacuum. For the small, scrappy birds that survived, this was an unprecedented evolutionary opportunity. With their main competitors and predators gone, they were free to radiate out from their survival niches and diversify into the vast array of empty roles left behind. In the millions of years that followed, they exploded in diversity, evolving into the 10,000-plus species that fill our skies today. The sky had been inherited by a new dynasty, one that would play by a completely different set of rules. The age of the reptilian giants was over, and the age of the avian masters had begun. The colossal shadow of Quetzalcoatlus has never again graced the surface of the earth. For 66 million years, a span of time almost incomprehensibly vast, the throne of the sky's largest flyer has remained conspicuously vacant. This simple, stark fact presents us with a fundamental and deeply compelling question that brings our story directly into the modern world. Why? Why has evolution, in all its relentless, diversifying ingenuity, never managed to rebuild a flying creature of that same staggering magnitude? The answer is not a simple one. It is a complex tapestry woven from the threads of atmospheric chemistry, the brutal realities of evolutionary competition, and the subtle but unbreakable constraints of biomechanics. And in exploring these limitations, we begin to uncover a startling and provocative truth. The next giants might not be what we expect at all, and some of them may already be hiding in plain sight. One of the most persuasive hypotheses for the modern absence of flying titans relates to the very air we breathe. The Earth's atmosphere is not a static entity. Its composition has fluctuated dramatically over geological time. By analyzing ancient air bubbles trapped in amber and using sophisticated geochemical models, scientists have pieced together a history of our planet's air. This history reveals that during certain periods, particularly the Carboniferous and Permian around 300 million years ago, atmospheric oxygen may have comprised as much as 35% of the air, compared to the 21% we have today. This oxygen-rich environment is widely believed to be the primary reason for the existence of Paleozoic giant insects, like the dragonfly-like Meganeura, which boasted a wingspan of 75 centimeters. The physics are straightforward. Higher oxygen concentrations make the process of respiration and energy metabolism vastly more efficient. For a flying animal, this is a game-changer. Flight is one of the most energetically expensive forms of locomotion imaginable. More oxygen in the air means more metabolic horsepower available to the muscles, allowing for larger bodies and more powerful flight strokes without a corresponding increase in the mass and volume of the respiratory system. It's like switching an engine from low-grade fuel to high-octane racing fuel. You get more power from the same engine size. While the atmosphere of the late Cretaceous wasn't as oxygen-rich as the Permian, it may have still been sufficiently different from today's to provide a crucial advantage to large flyers. The subsequent drop to modern oxygen levels may act as a subtle but firm physiological ceiling on the maximum size a flying vertebrate can attain. The engine of life simply doesn't run on the same premium fuel it once did. But perhaps an even more significant barrier is the sheer force of evolutionary competition, what biologists sometimes call the tyranny of the incumbent. The pterosaurs, especially in their early history, evolved into a relatively empty sky. They were the pioneers, the birds that survived the KPG extinction, however, inherited a world cleared of its masters, a clean slate. They exploded into this ecological vacuum, rapidly diversifying and perfecting their own model of flight. They became masters of every conceivable aerial niche. The Cenozoic era, the age of mammals, has, in the sky, been unequivocally the age of birds. Today, the skies are crowded with over 10,000 species of highly specialized, incredibly efficient avian experts. This creates an almost insurmountable evolutionary barrier for any potential new giant. Any creature attempting to evolve towards large size today would have to run the gauntlet of this intense competition at every single stage of its evolutionary journey. A fledgling flyer the size of a pigeon would have to compete with actual pigeons, falcons, and owls, all of which have been perfecting that niche for millions of years. A medium-sized flyer would have to contend with gulls, crows, and hawks. The evolutionary ladder to gigantism has had almost all of its lower rungs kicked out by these established, hyper-efficient masters of the air. It's hard to become king of the sky when every corner of the kingdom is already ruled by a fiercely competitive baron. These powerful constraints of atmosphere and competition have defined our modern aerial world. They have drawn a firm line in the sand, dictating what is and is not possible. And yet, nature is endlessly creative. When one evolutionary highway is blocked, it often finds a surprising detour. This brings us to the most provocative part of our story: the search for the next giants that are already among us. If we are willing to redefine our concept of a flying giant away from the specific model of Quetzalcoatlus and instead look for surprising, boundary-pushing feats of aerial locomotion in large animals, we find some truly astonishing candidates. Our first, and most shocking, hidden giant comes from the rivers and lakes of Africa: the common hippopotamus. It is the very antithesis of an aerial creature. It is a massive, water-loving heavyweight, with some individuals tipping the scales at over 3,500 kilograms. The idea of a hippo flying sounds like something from a surrealist painting or a children's cartoon. Yet, recent biomechanical studies using high-speed video analysis have revealed something that defies our expectations. When a hippo runs or trots at full speed, its immense leg muscles generate such an explosive amount of force that, for brief, measurable instants, all four of its feet leave the ground simultaneously. In that moment, for a fraction of a second, the hippo is fully airborne. This is not flight in the sense of soaring or flapping, of course. It is a moment of pure ballistic aerial locomotion. But it is a profound testament to the sheer power that can be generated by biological muscle, a force sufficient to hurl a multi-ton body into the air, even if only for an instant. It demonstrates that the raw physical potential for aerial movement exists even in the most unlikely and massive of modern body plans. It forces us to broaden our definition of flight. Is it only the sustained, winged locomotion of a bird? Or is it any process by which a living creature temporarily defeats gravity to move through the air? The airborne hippo is a living demonstration of untapped power, a hint of the physical potential that still resides within modern vertebrates, waiting for a different evolutionary pressure to express it in new ways. Our second category of hidden giants is more widespread and conventional, yet it represents a strategy so successful that it has evolved independently dozens of times across the animal kingdom: the masters of gliding. Powered flight is metabolically expensive. It requires a huge and constant input of energy. Gliding, on the other hand, is a masterpiece of energy efficiency. It is the art of falling with style, of using a simple airfoil to convert the potential energy of height into the kinetic energy of horizontal movement. It is a different, but equally valid, solution to the problem of navigating a three-dimensional world. We see this strategy perfected in an incredible diversity of forms. There are the flying squirrels, who stretch a furry membrane of skin called a patagium between their wrists and ankles, transforming their bodies into living wingsuits to navigate from tree to tree. In the rainforests of Southeast Asia, the Draco lizard, a small reptile, can flare out its elongated ribs to create a pair of makeshift wings, allowing it to glide for remarkable distances. Even more bizarrely, the paradise tree snake of the same region can launch itself from a branch, flatten its entire body to create a concave airfoil, and actively undulate through the air, exerting a surprising amount of control over its trajectory. These creatures are not true flyers in the powered sense, but they are masters of a different kind of aerial locomotion. They are the living embodiment of an alternative evolutionary pathway, one that bypasses the intense competition of the bird-dominated sky. They are the unexpected flyers, the next giants you've never heard of, not because of their size, but because of what they reveal about the enduring, creative potential for life to conquer the air in ways we are only just beginning to fully appreciate. The story of the flying giants has, until this very moment, been a narrative written by biology and deep time. It has been a saga of natural selection, of evolutionary pressures, of adaptation, and ultimately of extinction. But here, our story is about to take a sharp and definitive turn. We are leaving the realm of what life did and entering the world of what humanity can do. The lost blueprint of the pterosaurs, locked away in stone for 66 million years, is no longer solely the domain of paleontologists deciphering the past. It has been discovered and is being actively decoded by a new kind of explorer, the engineer. We are now entering an era where the next generation of giants to fill our skies will not be the product of a million-year-long evolutionary process. They will be designed, built, and flown by us. The secrets of impossible biology are being reverse-engineered to create the flying machines of tomorrow. This fusion of ancient life and modern technology falls under a burgeoning scientific discipline known as biomimicry. It is a philosophy of innovation that seeks sustainable solutions to human challenges by emulating nature's time-tested patterns and strategies. The core idea is that life, over 3.8 billion years of research and development, has already solved many of the problems we are grappling with today. Instead of inventing from scratch, biomimicry suggests we should turn to the natural world's library of perfected designs. And in the realm of flight, the pterosaurs represent one of the most advanced and inspiring chapters in that entire library. The transition from paleontological curiosity to tangible engineering application begins right where we left off, deep inside the fossilized neck bone of that giant Asdarchid. That intricate helical network of spoke-like trabeculae, which provided such astonishing strength for so little weight, is more than just a biological marvel. It is a blueprint for a revolution in materials science. For decades, engineers in the aerospace industry have pursued the holy grail of creating materials that are simultaneously ultra-strong, damage-resistant, and incredibly lightweight. Every kilogram saved in an aircraft structure is a kilogram that can be allocated to fuel, cargo, or passengers. The pterosaur neck demonstrates a near-perfect solution. Using advanced computational modeling and additive manufacturing, more commonly known as 3D printing, engineers are now creating and testing structures that replicate this biological design principle. Imagine the internal support spar of a future cargo drone's wing. Instead of being a solid I-beam of aluminum or a simple carbon fiber composite, it could be a hollow tube with a complex, 3D printed internal lattice that precisely mimics the trabeculae of a pterosaur vertebra. Such a design could be dramatically lighter than any conventional spar, yet stronger and far more resistant to buckling and catastrophic failure. The graceful neck of a long-dead reptile is providing the direct inspiration for the next generation of aerospace materials. The inspiration, however, extends far beyond just materials. The entire flight apparatus of the pterosaur is a rich source of engineering insight, particularly its unique, shape-shifting wings. The rigid, static wings of most modern aircraft are a major compromise. A wing shape that is optimized for efficient, high-altitude cruising is inherently inefficient for slow-speed takeoffs and landings. A wing designed for high-speed, agile maneuvers is terrible for long-distance soaring. This is where the concept of morphing wings enters the picture, a major frontier in modern aeronautics research funded by agencies like NASA and DARPA. The goal is to create aircraft that can actively change the shape, area, and curvature of their wings in mid-flight. This is precisely what pterosaurs were doing 100 million years ago. Their complex wing membrane, supported by the unique pteroid bone at the wrist and stiffened by the network of actinofibril fibers, was not a passive sail. It was an active, controllable surface. By subtly adjusting the tension in the muscle layers within the membrane and changing the angle of the pteroid bone, a pterosaur could alter the wing's camber to maximize lift at low speeds, flatten it to reduce drag while soaring, and make fine adjustments to maintain control in turbulent air. Engineers are now studying the biomechanics of this system to develop smarter, more responsive skins for their own morphing wing designs. These could be made from flexible composites embedded with actuators that allow the wing to change shape seamlessly, creating a single aircraft that can be a high-speed jet, an efficient cruiser, and a stable landing platform all in one. The pterosaur wing is teaching us how to build more versatile and efficient flying machines. Even the way these giants broke the bonds of gravity is inspiring new technology. The sheer power and mechanical elegance of the quadrupedal launch is being studied for its potential applications in robotics and drone technology. Consider a large, heavy-lift drone designed for disaster relief, tasked with delivering medical supplies to a remote, mountainous area with no available runway. The ability to launch from a standing start using a powerful, explosive vaulting motion inspired by Quetzalcoatlus would be a game-changing capability. It would free large unmanned aerial vehicles, UAVs, from the tyranny of infrastructure, allowing them to operate in the most challenging and inaccessible terrains on Earth, or even on the rugged surface of other planets like Mars. But the lessons from nature's flyers are not confined to the deep past. The animal kingdom today is a living library of aerodynamic solutions, and sometimes the most profound insights come from the most familiar of creatures. For a long time, a key aerodynamic principle known as the leading edge vortex, or LEV, was thought to be the special trick of insects. An LEV is a small, stable whirlwind of air that forms over the top of a wing during a flapping motion. This vortex creates a pocket of extremely low pressure, which sucks the wing upwards, generating surprisingly high levels of lift. It's the secret that allows a bumblebee, which by all conventional aerodynamic standards is too heavy and has wings too small to fly, to get off the ground. For years, it was assumed that this high-lift mechanism was unstable and only worked at the small scale of insects. However, advanced smoke trail and particle imaging studies have revealed that bats, and even some birds, also use and control LEVs to enhance their flight performance, particularly during complex, agile maneuvers like hovering, sharp turns, or landing on a perch. This discovery has been revolutionary for the burgeoning field of micro-air vehicles, or MAVs. By designing flapping wing robots that can intentionally generate and maintain a stable leading-edge vortex, engineers are creating machines with an unprecedented level of agility and maneuverability. These bio-inspired robots can navigate cluttered indoor environments, hover in place, and withstand gusts of wind with a dexterity that no fixed-wing or rotary drone can match. The secrets of a bat chasing a moth are helping us build machines that can perform search and rescue operations inside collapsed buildings or conduct surveillance in complex urban environments. This is the power of biomimicry. It is a paradigm shift, a move away from the brute force engineering of the industrial age towards a more elegant and efficient approach inspired by the genius of nature. The next giants are taking shape right now, on computer screens in university labs and in the workshops of aerospace startups. They are cargo drones with skeletons inspired by pterosaur bones, fighter jets with wings that morph like a bat's, and tiny, agile robots that fly with the grace of an insect. They will not be creatures of flesh and bone, but of carbon fiber, smart alloys, and sophisticated algorithms. They will be the technological inheritors of a biological legacy that stretches back hundreds of millions of years. We may have lost the original biological blueprint, but we are now in the process of rewriting it, page by page, in the universal language of engineering. The sky is about to be filled with giants once more, but this time, they will be giants of our own creation. We have traveled from the primeval, humid skies of the late Cretaceous to the sterile, climate-controlled environments of 21st century engineering labs. We have resurrected the greatest flyers the world has ever known, decoded the secrets of their impossible biology, witnessed their cataclysmic demise, and discovered their ghostly echo in the bio-inspired machines of our own creation. We now stand at a unique and pivotal moment in the 4-billion-year history of life on our planet. A genuine crossroads where the future of giant flight could diverge down two vastly different, almost parallel, paths. The final act of our story, therefore, is one of grounded speculation. It is a look forward, guided by the scientific principles we have explored, to ask the ultimate question. Will the next true giants to fill our skies be a product of our own hands? A technological dawn? Or, on a much longer, more patient timescale, could biology itself orchestrate a biological echo, repeating the past and producing a new age of living, breathing titans? The first path, the technological dawn, is not a distant science fiction fantasy. It is an imminent and rapidly approaching reality. The bio-inspired flying machines we have discussed are the direct and immediate successors to the vacant pterosaur throne. Within the coming decades, we will witness the emergence of autonomous cargo drones with wingspans that rival, and may even exceed, that of Quetzalcoatlus. These silent, ultra-efficient gliders will navigate the stratosphere, following digital drone highways to deliver goods across continents with a fraction of the energy consumption of current air freight. Their internal structures, 3D printed lattices of advanced composites inspired directly by pterosaur bone, will make them incredibly light, durable, and resilient. They will be the new, unseen giants, the workhorses of a future global economy. This revolution will not be limited to cargo. The principles of biomimicry will fundamentally reshape human travel. We will see the development of passenger aircraft with fully morphing wings, their surfaces rippling and adapting in real time to changes in air pressure and weather conditions. These planes will not just be more fuel efficient. They will be safer, able to mitigate turbulence by actively changing their aerodynamic profile, much like a pterosaur adjusted its wing membranes in a gust of wind. In our cities, the principles of agility and maneuverability learned from bats and insects will give rise to a new era of urban air mobility. Small, quiet, electric vehicles capable of navigating the complex three-dimensional landscape of a metropolis with unprecedented precision. These will be the technological inheritors of a biological legacy, a sky filled with giants of our own making. These machines will represent the pinnacle of human ingenuity, a testament to our ability to learn from the deep past and apply its lessons to our own future. They will be faster, stronger, and more efficient than anything that has come before. But they will also be sterile. They will be creatures of code and carbon fiber, not flesh and blood. They will be a remarkable echo of the past, but an echo nonetheless. This is the most likely and the most certain chapter in the new age of giants. It will be a world where the ghost of Quetzalcoatlus flies again, but as a machine, a tool designed and built to serve human needs. It is a future defined by our own intelligence and ambition. But what of the second path, the far more profound and uncertain possibility of a true biological echo? Is it conceivable that, given enough time, nature itself could repeat its grandest aerial experiment? Could life, once again, produce a flying creature on the scale of the great Asdarchids? This question catapults us into the realm of deep time and grand-scale evolutionary theory, but it is not without a firm scientific basis. The primary constraints that currently limit the size of flying animals, our relatively lean 21% oxygen atmosphere and the intense competition from modern birds, are not necessarily permanent fixtures of our world. On a geological timescale, measured in millions of years, the Earth's systems are profoundly dynamic. Plate tectonics, the engine of our planet, constantly reshapes the continents and oceans. This, in turn, influences ocean currents and long-term climate patterns. Periods of increased volcanic activity can pump vast quantities of gases into the atmosphere, while shifts in the planet's carbon cycle, perhaps driven by the evolution of new types of plankton in the sea, can sequester or release immense stores of carbon and oxygen. It is entirely plausible that, millions of years from now, a new configuration of these planetary systems could lead to a sustained increase in atmospheric oxygen concentration. If the air once again became significantly richer in this vital fuel for metabolism, one of the main physiological brakes on biological gigantism would be released. The environmental stage could be set once more. If that were to happen, the only remaining barrier would be competition. The birds and bats of today are masters of the sky, a dynasty of incumbents that are almost impossible to dislodge. But the history of life on Earth is punctuated by mass extinction events. The KPG impact that wiped out the pterosaurs was just one of at least 5 major cataclysms. Another such event, whether from a future asteroid impact, a series of colossal volcanic eruptions, or a runaway greenhouse effect, could one day press the Great Reset button again. Such a catastrophe could devastate the incumbent rulers of the sky, clearing the ecological board and creating a new power vacuum. In the aftermath of such an event, in a world with a richer atmosphere and an empty sky, the evolutionary pathway to gigantism could reopen. This is the principle of the vacated niche. Evolution abhors a vacuum. When a dominant group is removed, it creates an unprecedented opportunity for the survivors. In this future world, a surviving lineage, perhaps a group of resilient, gliding mammals that weathered the extinction in burrows, or a lineage of bats, or even a hardy group of birds, could find itself in a world of boundless opportunity. With no competitors to hold it back and a surplus of food and space, the relentless pressure of natural selection could begin to favor larger and larger body sizes. Step by evolutionary step, over countless generations, this lineage could begin to scale up, rediscovering the ancient biomechanical tricks of hollow bones, powerful launch muscles, and efficient wing membranes. It is a process that has happened before, and the fundamental principles of biology and physics strongly suggest that it could happen again. The blueprint is not truly lost. It is merely archived in the vast library of DNA and evolutionary possibility, waiting for the right conditions to be checked out once more. So, we are left with 2 starkly different futures for the flying giants, a powerful dichotomy that reflects our own unique position in Earth's history. One is imminent, a technological dawn born from human ingenuity, a future of magnificent machines that pay homage to the biological masters of the past. The other is a distant, awe-inspiring possibility, a biological echo that whispers of the deep, cyclical nature of life, death, and rebirth on our planet. It is a reminder that the world we see today is but a single, fleeting frame in the epic film of life's history, and that the forms and dynasties we believe are gone forever may one day find a way to return in a new guise. As we finally look up at the sky, we see it now not just as it is, but as it was, and as it might one day be. We see the faint, ghostly shadow of a giraffe-sized reptile soaring on the thermal winds of a world lost to time. We see the glint of a future, bio-inspired aircraft, its design a direct and brilliant legacy of that ancient creature. And perhaps, if we look far enough into the deep future, beyond the scope of human lifetimes and civilizations, we can just begin to imagine a sky where new, living giants, born not in a lab but in the patient, relentless crucible of a future world, once again cast their magnificent shadows upon the earth. The story of flight is far from over. The next giants are, without a doubt, coming. The only question that remains is whether they will be a reflection of our own image, or a reflection of the planet's enduring creative power.